30? All right. Are you going to have to give me the specs on that coil? This is one of those things where we're just going to go ahead and calculate the inductance based on a formula. Then we're going to go ahead. This is a standard coil, right?
Yes, sir.
This is out of Stu Wentworth's book. He gives you the formula for this thing, by the way. So he wants the L of this thing. Go ahead. Hey, I'll tell you what. Let me go through this with inductors first and resistors. I want to go through the R, L's, and C's. Then I'll do this problem for you, all right? It's straightforward reading, but it's not a very tough. This isn't a very tough problem. Last time we talked about wires. We talked about stranded versus solid wires, and we talked about the internal inductance of a wire. There's one other thing we didn't talk about. There's a reason we didn't. It's called the external inductance associated with the wire. We did sort of when we had two wires separated at a distance. You all follow me on that one? But what we didn't do was talk about the general way to deal with wires and the actual impedance related, or the inductance of a wire. Now let me explain something whenever you're dealing with wires, the real problem. If you have a wire with a current I, right? Regardless of what else is involved in the problem, there's some H field. If I come out a distance rho away from there, there's an H field that's going to be present right here, right? It's either into or out of the board. Correct, class? Now that H field causes magnetic energy. You don't need to write this down, just listen. This is just a discussion to give you perspective. The H field causes a B field. The B field, I mean, they're one and the same. You get a magnetic energy density. Magnetic energy density is 1/2 times mu h squared, magnitude of h squared, or it's 1/2 times magnitude of B squared over mu, and that's in joules per meter cubed. Now just listen to me, right? Now, if you integrate that energy, this energy density, over the region of space it exists in, you find a total magnetic energy. Do you all follow me on this? So you would find the total magnetic energy by integrating over the volume that it existed in, which is literally all space, this magnetic energy density over the volume, dvol. And you get this. And you could set that equal to 1/2 Li squared. That's the total magnetic energy for an inductor. Follow me on this? Do you all remember that formula? 1/2 Li squared was the magnetic energy of an inductor. And therefore, if you knew the current, you could multiply by 2 and divide by I squared, and you could find the inductance. Now, here's the problem. Almost always, if you have two straight wires like this separated at a distance d, we can get the inductance by using the flux linkage method I mentioned last time, right? By finding the flux link between them. But in the general rule of thumb, you don't have that luxury. For instance, what typically happens if you have a power line, say it's a plus 7,200 volt line, and it comes to, it connects, right? And this goes into your house, or maybe not the 7,200 volt, goes into an industrial plant, and it comes down, and it's going to route like this, right? And then finally comes back up, and you're trying to figure out the inductance of that. Well, you don't know even where to begin, because the magnetic energy or the flux is not easily established. You don't know the linkage. Do you all follow me on this, class? So what they've developed is something called the partial inductance formula. And now it's only for external inductance. We know generally if you have a wire of a given length, if it's straight, all right, and I come out a distance rho from it, if I'm very close, I know what the magnetic field is here, right? I can get it. I can assume it's infinite. The further I go away, the more it looks like a short dipole in a sense, and I can get the magnetic field for that. I can pretty much establish the magnetic, I can find out what the magnetic field is there, the magnetic energy density, and I can do a straightforward calculation. Now that's assuming there's nothing next to it. Most of the time you're going to have a ground, and you're going to have filing cabinets, and you're going to have all sorts of other things around there that are metal, all right, that don't allow a magnetic field to penetrate it easily, a time-varying magnetic field. So now you have magnetic energy that's really hard to get a handle on how to integrate it, or flux linkage that's almost impossible to. So what they've done is establish something called the partial inductance theorem. And they say most of the energy is in the vicinity of the wire. I've never gone through this in detail. I want you to know this. But it comes down to this. They said we can estimate the inductance of wires even with filing cabinets near them and grounds and stuff like this, by saying using the partial inductance formula. And now you write this down, it's in the book. It says L, this is for partial inductance. And I might add, this has to do with a wire of length L, straight wire. It's assuming it's straight, of length L. Forget the wire gauge, it doesn't matter. It's going to say it's equal to, this he uses 2 times 10 to the minus 7th. Other books use they have a different constant for this. And then they adapt a different constant in the equation, times the actual length of the wire. And I better use a small l here, we'll get confused. That's the length of the wire. This is all in meters. And then it's going to be times the natural log of 2 times the radius of the wire over, I'm sorry, 2 times the length of the wire over the radius of the wire minus 1. And that will be in henries. Now, this is a formula I don't expect you to memorize. There's versions of this. I want to tell you that that constant sometimes is different, and in here you might see something slightly different. So this is one of many formulas, but it's approximate. It gives a good idea of the external inductance of wires of length L, where they're not on top of a ground, but they're more or less in a region that would be otherwise almost impossible to calculate. Consider it above a ground plane at least by a distance of, say, probably at least 5 radii above the plane. All right? And this will give you an estimate of it, but it's very hard to calculate. I've never read the entirety of this, but partial inductance is something that you use a lot of times when you're building things to get a first order kind of guess at the effect of the inductance of a line. Okay, now, next. The next thing I'm going to talk about is when we're talking about different elements, what they are and what they aren't. I think I talked a bit about the resistor, right? Did I go through the whole 9 yards of it? Well, I'm going to go through it again. By the way, partial inductance is something, if I ask you a question about it, I'll give you it, all right? If I ask you the total inductance of something, and if I say use the partial inductance formula, I'll provide that. I don't expect you to memorize that one. All right, now we get into the elements. And I've told you, gave you a little background, that nothing acts like it should at high frequencies. And that's the general thing you always believe. Nothing behaves the way it should at high frequencies when you come to electronic components. Especially things. I actually did this last time. I talked about a resistor R, and I said that resistor, in a sense, is something that you associate with a piece of carbon, right? It's simply a cylinder of carbon with red and black, with stripes on it, to give you the idea. Really, resistors look like anything. From there, I said, what does a resistor really look like? Well, you start always with the element itself, right? R. And then there's going to be a capacitance. The reason there's a capacitance, there's charge buildup on either side, right? Plus, minus Q when you have a plus, minus V, correct? So there's some associated capacitance. You can't get around it. There is. There's also, the inductance has, the wire has inductance, so there's an LX associated with this. Both the C, I call it CX. Anytime you see an X, it means you wish it wasn't there. To me, that's the way I look at this. These are things that are parasitic. They're parasitic capacitances, parasitic inductances. You wish they weren't there, but they are. So when you look at this element, this is where I was Friday. I said if you look at the impedance right here, Zn of this thing, what we'd like to do is plot it. Now, what I'm going to show you is a typical kind of plotting. It's a Bode plot of this, and this is done for all components. There is one thing I said about this model, too. That is an estimate, right, of what it looks like. In truth, you know that the inductance here is a function of frequency. We just figured that out, right? The inductance is a function of frequency right here, which means this model kind of breaks down. Also, the capacitance is a function of frequency. So this is just a first order cut at it, but they pretty much look this way. I've done this a lot in EMC, seen things. So when you look at this input impedance right here, well, what is Zn? It's equal to J omega L, right? Or SL if you want to use the S domain. And then it's going to be plus, and really it's going to be these two. So it's going to be R times, it's really R over j omega c over r plus 1 over j omega c. And if you multiply top and bottom by j omega c, which I'm about to, you get this. Is that right? Wait a second. Yeah, I believe that's right. Okay, now when you look at this, if you let omega go to 0, you see it's just r. You all see that in that equation? In general, if you move the equation, this is what it'll look like when you plot it in this way. If you put the frequency here, but write down the log of the frequency. So in other words, if this was 1, this would be 10, this would be 100, this would be 1,000, and so forth. And then you get your demarcations like that. And you know what I'm talking about, right? On this axis, almost always, it's 20 times, either the log or 20 times, actually, do just the log of the magnitude of Zn. And I'm going to talk about that in a second. So it's the log of the magnitude. It could be 20 times the log of the magnitude. It would be stated in the journals that you see what it is. And the reason is 20 is just a scale factor. Because this is not a voltage or a current, it really doesn't need that. So when you plot this, it always looks like the resistor here. This value would be the log or 20 times the log of R. And it stays there until it hits its first cut frequency. I call it a cut frequency or break frequency. And this frequency is going to be 1 over, and this would be 2 pi times R times Cx. That's the first frequency. And it's going to start going down after that part. Because here's what happens here. That's when this all of a sudden becomes a factor, if you follow me on this. Now, when all of a sudden j omega r times c equals 1, then I have 1 plus j1. That's the point when we come down. If you take the magnitude of 1 plus j1, it's the square root of 2. It's always going to be square root of 2 is the break frequencies on all these things. Whenever you get a square root of 2, increase or decrease. Do you all follow me in this class? You remember this from signals and systems? And from, I don't know if you had it in circuits or not. How many do? All right, so that's the reason I put it this way. I can take a look when omega times c times r equal 1, and that's really going to be when omega is equal to 1 over rc, or f is going to be equal to 1 over 2 pi rc. Does everybody see this, class? Give me a show of hands if you do. All right, omega is always 2 pi f. All right, and what we're looking for is when this all of a sudden becomes 1, omega times c times r. Did everybody follow me? That's the first break frequency. It keeps going down at this rate until it hits this point, and this is going to be the resonant frequency, and that's just 1 over 2 pi square root of LC. You're familiar with resonance. This is LXCX, right? And then after that, it starts going up at a rate, and the rate it comes down. Now, if you put the 20, you can put the 20 on there, because I guess Wentworth's going to do that probably. This will fall at minus 20 dB per decade. And that's the real reason they put the 20 on, because they'll get it, they know these rates of fall and increase. And then on the other side, once we go past the resonance, it'll go up at plus 20 dB per decade. But I have seen it without that 20 before, too. Following on this? Now, what could I ask about this? If I said, if the resonant frequency was such and such, and the low frequency break was such and such, and R was such and such, you should be able to tell me what C and L are. Do you follow me, class? And it will always follow this shape. I'm going to give you problems like this tonight once I go through these. Everybody got that? So that's the shape of what a resistor's profile would look like versus frequency. And it's pretty straightforward. If you actually get into this, if any of you do development with exotic materials, high energy capacitors or stuff like that, you may see models that actually resistors that are made of exotic materials or anything like that for heat dissipation. You may see other inductances and capacitance that they introduce to account for other effects. But this is the most common model for resistors, and it's used everywhere as far as I can tell. The next one has to do with I'm going to do the inductor next, because that was a problem you asked me about. But the actual inductance is from a straightforward calculation. When we have an inductor, L, and we want the impedance of it right here versus frequency, you're used to thinking of an inductor as just a bunch of wind. You take, did you have to make inductors and measure them or not? You did? I haven't done it in EMC in a while. But normally, what you do is they take something that's got an iron core of a certain radius, and then they start wrapping shellacked wire on, maybe 100 windings. And then you apply a certain voltage at a given frequency, maybe 1,000 hertz, and you measure the current drawn by that. Then you can figure the impedance. Now, has anybody ever done that kind of thing? All right, did you do it in physics or engineering?
I did my co-op.
Where'd you do yours? Hobbies. Did anybody do it in a class or for a lab? Yeah.
There's something similar to that in physics too.
You did in physics too? Good. I'm glad to hear that. You should have had at some point somebody request you to actually estimate the inductance and then measure it from a formula and then measure it to prove it's either right or wrong. And that's it. Yeah, but did you measure the impedance of that thing? Does anybody remember? You didn't? Did you measure the? You didn't measure it? Resonance would be 1 over the square root LC. All right, well, at least you measured something. You found the resonant frequency. What? Oh no, it wasn't something you actually did though.
No, we built an antenna out of a pizza box, and then we built the spectrum analyzer.
For who?
This is radio.
Okay, well, if you hooked it up to the spectral analyzer, you saw resonance, right? And then could you estimate from that other parameters or not?
We didn't ask.
Okay.
We can't estimate C.
What?
We can't estimate C. We don't know the capacitance. We didn't add it. It doesn't necessarily have the capacitor.
All right. I guess nobody's ever measured, proved inductance. It's a good thing to do, especially because it's so easy to do. All right. Anyway, that's an inductor. But in truth, an inductor can look like almost, for instance, if you talk about something that's modeled as an inductor, at low frequency, there are almost always coils of wire. Almost always. However, if you get to like VLSI designs, if for some strange reason they needed it, they're usually spirals. They can't build inductors out of the board. So they'll spiral into the board. They'll just have a little spiral going in there. And that's also an antenna that looks that way, but so it depends on the frequency. But inductors generally are coiled wire, not always. So what does an inductor look like at high frequency? It always starts at a coil of wire, right? But then within this coil, because there's a lot of wire, there's going to be a resistance. It's a parasitic resistance due to the length of the wire. But you have to understand the voltage that's developed across that inductor is not only because of the inductive energy, but it's also because of this resistance. So generally then, the capacitance is here that's shown across it. It's outside of where the resistor is. This is L, this is C. So the actual capacitance is undesired, but this is going to have a capacitive reactance of 1 over j omega Cx. This has an inductive reactance of j omega L, and this is just R. So when we look at the impedance between the ends right here, and we measure Z on this one, well, you can see it's going to be this in parallel with this, right? You agree with me? So you can say that the Zn on that one is equal to, depends how you want to do it, I can say it's going to be 1 over that, or j omega times Cx, plus 1 over this. So it would be 1 over, and then it would be Rx plus j omega L. And that would be the actual impedance of that thing. And that should look right. Now, what you'll see is at very low frequencies, just observe this with me. Let omega go to 0. All right, omega goes to 0, that goes away. Do you agree with me? Omega goes to 0, that goes away. The only thing left is 1 over Rx over 1, or it's Rx. Do you follow me? So the impedance of an inductor at absolute no frequency, a DC, if you got an ohm meter and measured it, would be the DC resistance of the wire. That's it. And it's usually very, very, very small, like milliohms or less for most inductors. Now, as frequency goes up, all right, it keeps going up and up and up until you hit resonance. There is no 3 dB frequency. It keeps going up and up and up until all of a sudden you get a resonance between here and here. I can prove this to you, but it's nice to know that's what you need to look at. So when you look at the actual graph versus frequency, and this would be logarithms of frequency, typically like 1, 10, 100, 1,000, and 10,000, so forth like that. What you're going to get is something, it's going to come in and it will look just like an inductor's impedance. Well, that's 1 over j omega L is, or sorry, j omega L, pardon me, j omega L is the impedance of an inductor. Correct, class? So that's just going up at 20 dB per decade. So on this axis, if you plot 20 times the log of the magnitude of Z, you'll see it's going to go up at a continuous rate of plus 20 dB per decade until it hits resonance. And resonance will be 1 over 2 pi square root of L times Cx. And on the other side of that, it'll come down at minus 20 dB per decade. Now, the reason I didn't show, the bottom line theory, the milli, like whatever it is, milliohm, the 20 times the log of Rx there at 0, is because almost never you worry about 0. The next one down here would be 0.1 and then 0.01 hertz. All right, it keeps going down. You never see 0 in there. So don't even worry about any kind of low-cut frequency on this. Remember this, the inductor just looks like a pinnacle, all right, something going to a pinnacle, and you have to worry about the resonant. Follow me on this, everybody? This is in the book, by the way. This is not hard. So that's an inductor. If you want to prove it to yourself, you can plot this thing. I like doing this. When I do this, I usually use S, not J omega, and I can modify this and make it a much easier thing to plot. This is what the plot will look like when you go to resonance. Next, after this, I'll do this one over here. See if I have a better marker too. Well, I'll do it here. When we talk about the actual capacitors, well, capacitors are, when you had your laboratories, didn't you have little disc capacitors for the labs? Did anybody, well, capacitors come in all sizes and shapes depending on their use. Has anybody ever seen large high-energy capacitors around here? One person? Capacitors can be as tall as I am and probably 3 or 4 foot by 3 or 4 foot. Things at the power stations and stuff like this. Almost always a capacitor is really created by just taking a conductor and some insulator, something that prevents arc over between it, and then another actual conductor that's plus minus, and they just roll it up. As a matter of fact, has anybody ever made a capacitor in here? They don't do this anymore. If you take aluminum foil, it's cheap, right? Roll out about a 2.5, 3 foot section of it. Then take wax paper. Make sure the aluminum foil is cut so the width is a little shorter than the wax paper, so the wax paper overlies it. Take wax paper, roll it on there on top of it. Then cut it. Then take the same aluminum foil and put it on top of that. Now make sure the inner aluminum foil doesn't touch the last one. And then what you have to do is make sure when you cut that aluminum foil that there's wax paper between them all the way. Take it and roll it up. Just roll the thing up. And then take a couple of pins and put them on the inside on one and the other thing. And then take like a 5-volt battery, 10-volt battery, and charge, or should say, it's nice to get a larger amount of DC voltage. You can charge it up, and when you discharge it, you're going to see a spark. That's the simplest capacity. You can estimate the capacitance. I think most people know how to do this, but it's a nice, useful tool for kids like in grade school and high school to do that. C is equal to approximately epsilon A over D. Well, you know the thickness of the wax paper. You know that you can look it up. The dielectric constant of wax paper, I don't even know that off the top of my head. But you can sure look it up. And then you can calculate the area because you just built it. And by gosh, you can figure out the capacitance. And if you take that same thing, charge it up, and put a resistor of about 100 or 200 ohms on it, and then you look at the voltage decay across that capacitor versus time, next time when you hook it up, you get a decay parameter, and you can actually estimate the capacitance and prove that, in fact, what you have is about right, because with a known resistance. You know what I'm talking about, that it decays as 1 e to the minus t over RC. All right, so you can do that kind of stuff. That's how I think of capacitances, but they have all sorts of shapes and sizes. But they're always plates separated by distance. The thing is, I mean, they can be wound like I just showed you there, or they can be arranged in any form, but they have to have 2 insulated plates, all right, that they can charge up. And the closer they are, the larger the capacitance. The way they model a capacitor is this usually. They start with a capacitance like such, and they say that's the way it is. Now, in truth, there is some leakage resistance, but except for electrolytic capacitors, they ignore that. Most capacitors that are made with good dielectrics that are not electrolytic, the reason they use electrolytic is they can store a huge amount of charge very cheaply. In other words, they have the potential to cause a dielectric constant that is very large. And electrolytic capacitors cannot have current run into them the wrong direction. All right, they can only have there's a certain polarity of voltage that has to be maintained. Remember that about electrolytics if you're around them. If you don't, it'll blow up. And has anyone ever seen them blow up around here? You have? Yeah, we used to do it for fun. When I was in electronics lab, I remember that. And I never had anything dangerous happen, but some of them can be noisy. So that's the capacitor. The model we're going to use, we're not going to do anything with a resistor in there and parallel with it or anything. Normally, because there is wire involved, you're always going to have a lead inductance that's unwanted. And whenever you have wire, you're going to have a resistance, R. It's just the nature of the beast. And that's really Rx. So that's really what the actual capacitor looks like, the model. And they're easy to get confused. But on a curve, I mean, if you look at this in the frequency domain, the impedance of this is what? Well, ZAB here is just equal to Rx plus J omega L, right? Plus just 1 over J omega C. And if you look at this versus frequency, and this would be logarithmic, so 1, 10, 100, 1,000, 10 to the 4, 10,000, and then here, 20 times the log of the magnitude of Z. This is the neat thing. The capacitor, all of them at low frequencies look like what they're supposed to be, right? All of them look just like they're supposed to be at low frequencies. Well, what's the impedance of a capacitor at low frequencies? Just 1 over J omega C, right? What is the value of that at 0? It's coming in at infinity, right? So it's coming in at a rate, it's inverted, it's the inverted inductor of minus 20 dB per decade. That's how fast it's coming in that way. Then it's going to hit a resonance. That's more than 20 dB. Let's do it that way. It's going to hit resonance. That's the only other frequency you worry about. That's 1 over the square root of LC, LXC times 2 pi. This is in hertz. And then it's going to go up at plus 20 dB per decade. That's just it. By the way, this is something just for your benefit, because I know sometimes people forget this. When I'm talking about 20 dB per decade, let's think about this. First, the actual impedance of a capacitor at low frequencies is 1 over J omega C. Does everybody agree with that, first of all? Now, if you take a look at 20 times the log of the magnitude of Z sub C, that would be 20 times the log of the magnitude of 1 over omega C. You can forget the actual J, right? And that's really equal to 20 times the log of 1 minus 20 times the log of omega, right? Minus 20 times the log of C. Isn't that right? I can break out the log C separate, can't I? Log AB is log A plus log AB is log A plus log B. Do you all agree with this? Now, this is a constant. Do you all agree with that? What's the log of 1? 0. It goes away. So when you look at this, every time you go up an order of magnitude, start with omega equals 10. Well, log of 10 is 1, it's minus 20, right? Now I go up a decade. A decade is a factor of 10, correct, class? I go from 10 to 100. Log of 100 is 2, correct? 2 times minus 20 is minus 40. It went from minus 20 to minus 40, which is 20 dB per decade. That's where it comes from. I don't know. People sometimes don't see that. I want to make sure everybody does. Got it, everyone? If it went up 40 dB per decade or down 40 dB per decade, then if you went 1 order of magnitude like I'm doing here, you would get a total of 40. That's what I mean by dB per decade. All right. That's that. Oh boy, I'm not going to get to where I wanted to go, but that goes without saying. All right, quiz time. So, yes, it's that time of day again.